that I just didn't believe would be possible within my own lifetime. And something that impressed me most in, this millennium was a discovery that one could find this kind of unstable structure that we've been studying in very few dimensions, let's say for Lorentz attractor, that they could be computed and experimentally discovered. You start in 61,506 dimensions. And this is a little bit like throwing a boomerang. A very skillful person in 3 dimensions can take a boomerang, throw it, and boomerang will come back. Now, in 4 dimension, it's much harder to do that, just because likelihood in coming into the same neighborhood becomes less the harder the dimension is. We never thought it would be possible to do this, but it is. And I'll give you some flavor for how it works in this tutorial. And the deal with this tutorial, you don't need me, you could do it yourself. If you're a professor, you could do this in 10 minutes. This will be a tutorial that doesn't have many equations. I mean, we can pull them up if we need them because there are links to them. But it's really a conceptual tutorial, and it's based on movies, video clips, simulations. I will not show the experimental data, even though some of it's very amazing. I just try to focus on the main idea of how is it possible to do this. And the main point of this tutorial is to tell you that when you think of the problems like motions of fluids or atmosphere or what happens at the edge of a black hole, we humans tend to try to visualize them in 3 dimensions. And that's totally sensible because we have a very, well-developed apparatus, both for observing them and interpreting them. Our brain can make sense out of them. And the thing that one has to learn, which is very much unlike engineering way of thinking about fluids, I'll take fluids as a very concrete example, is that you should actually visualize things in state space, which in this case will mean 65,000 dimensions. And that seems very crazy because we have a hard time visualizing things in 4 dimensions. But this tutorial hopefully will give you some sense how it works. To make it very specific, we will illustrate everything by so-called plane Cuet flow. So the idea of Cuet flow is that you have 2 infinite surfaces, bottom and the top, and they're counter-moving, and it's natural to go to the frame where they're counter-moving with the same and opposing velocity. And the effect, so the top one here is going away from us, and that's indicated by the red color. So whenever you see a red color, that means streamwise velocity that's going away from us. And whenever you see a blue velocity color, that means the liquid is going toward us in this particular visualization. The important directions are streamwise. Most physics will take care in this shearing direction. That's where things really happen. Very important parameters of the systems is the wall normal distance. And the problem can be rescaled in such a way that there is a number called Reynolds number, which will be studied in these examples in so-called transitional regime. This means the regime is when you see structures in this plot. And let me explain in more detail what this plot is. We see a plane that's a mid-plane between the two walls. And in that mid-plane, the velocity of fluid is three-dimensional, but mid-plane, it's two-dimensional. It has two components. And that's what these little arrows are. So when you see a bunch of arrows goes around, there is some kind of twirl in velocity field in the midplane. We also cut the fluid. It's in principle infinite in streamwise and spanwise dimensions, but in practice, we make it finite. And to be able to solve these problems, we even make it periodic. So we impose boundary conditions. The state of the fluid is same on this vertical normal cut to the fluid as over there. And now you see in a two-dimensional velocity field, and the color, the third dimension, gives you actually the third component. So in this cut, you actually see at one particular section of the flow, the full velocity of the flow. And then there are streamwise directions. You can see them here that we also cut the flow and make it periodic. And that's not terribly exciting dimensions. So that's what the color plot means. So this is a natural visualization because when the flow starts getting turbulent, then the fluid will be going between the walls and it'll be crossing this mid-plane. So that's a nice place to look at it. You can make nice experiments, and I will actually show you the experiment. I think it's nice to see it. So here is one particular experiment that studies shear flow. So this is Mark Avila. This is a big machine that looks like a printing press. It has two big cylinders, and hidden from the view four thin cylinders, whose purpose is to bring this plastic sheet so it slides against this glass wall in one direction on this side and the other direction on the other side. And then there is a bunch of electronics, lasers, etc., cameras that will maybe take a volume in the middle, let's say 1 liter of fluid here, and measure precisely what's happened to it. So it can be measured. And you can simulate it. That's another reason why we like these flows. They are relatively easy to simulate. So the way the simulation works, because of translational symmetries, in streamwise and spanwise direction, it's natural to describe a fluid velocity field in terms of its components, Fourier components. And in wall normal direction, it turns out one uses Chebyshev polynomial, but basically it's a very fast code you can write. And after I'm done with this, you can actually download the code from the link on this website, and you can do turbulence at home on your laptop. You can do this. Now, what you see here is, Reynolds number is 400. It doesn't really matter what this number is, but geometrical meaning is that the structures that you see here are comparable with the spacing between the top wall and lower wall. When the Reynolds number gets higher, the structures get smaller and you get more and more resolution. And many people obsessed with very high numbers, let's say 2 to Reynolds, which is the 2 to the 12, in which case, you would be just seeing stuff that's turbulent and very thin walls. That's out of the reach for the theory I'll describe today. What I want you to see from this picture is that when you run this kind of simulation, it never stops. And what you see is occasionally seems to want to get very ordered. You're shearing it, it seems to want to design some rolls. So you say, okay, that's boring. There was a transient and turbulence seemed to be there, but actually died. But it's not so. You approach this transient state, and then things go bam, and the whole thing explodes, gets very turbulent. And the task of this presentation is to tell you how to think about it and how to describe such a thing. So this is what we want to describe. And the striking thing about this, and I've emphasized it a number of times in this course, is that it's rich in recognizable patterns. In this case, they call streaks, rolls, vortices, etc. Now, in practice, we are not able to simulate accurately very large cells. And, the unwritten part of Cuet's book and convincing part of this course is to tell you, yes, we can do very large cells. But when you do simulations and you don't have a good theory, what people do is they say, well, when I look at this thing, I see that there is a characteristic scale. It's roughly the distance between the walls in this case. So can I make something that captures one of these or two of these rolls, and it's relatively small, so I can compute it? That's called a minimal cell. So what people do, and that's very empirical and not rigorous at all, is they have their nice codes that simulate Navier-Stokes equations, and they make the streamwise direction as short as possible and the spanwise direction as narrow as possible, but not so short and small that everything dies. So they play with parameters, geometrical parameters of the system, until they find a system that seems to capture the main things you've seen in a large simulation, which is there are periods where everything is going bananas, they look turbulent. And then there are periods where the system, you'll see this in a second, tries to organize itself. Like right now, it looks like a stable roll, and then it falls apart. And this repeats itself forever. And we cannot prove it mathematically. We cannot prove that this eventually doesn't become something that's steady and not turbulent. But in numerical and physical experiment, this goes on forever. So the striking, yep.
Yeah. So in the previous movie, right? So we're
this one,
right?
Yeah,
the small one. So how can I see the rolls here? So you said
they show up every so often. We'll get to them right now. Oops, looks very regular, and then it falls apart.
The roll, it means that it's actually there's a vortex, so there's some kind of
yes. So it looks like that fluid has organized itself in such a way that there are counter-moving rolls, and you're moving fluid from the bottom to the top, depending on the direction of the rolls. And these kind of solutions are very typical for flows which have this funny aspect ratio, is the ratio between geometrical dimensions. So one of these very stable rolls happens when you have some good olive oil in your frying pan, a thin layer, and you heat it. And you might observe that it actually arranges itself in a stable hexagonal pattern. And some of the stellar, and sun flows tend to make helical cells. So this is an example where you think the thing looks irregular, but it actually settles itself in a regular flow. But we are beyond that. It turns out this flow that looks regular is unstable. and we only approach it and then we run away. And I'll have more illustrations of that.
Yeah, just one question about the maybe the color coding here. So where do I see this raw motion from the colors here? If I do
what you see is that the top is on the whole following, it's red, so it's following the top part of the fluid is glued to the sheet going away from us. The blue one is the sheet that's going toward us, top and bottom wall. But then in between, you discover that fluid is going, for example, on midplane, there are parts of midplane fluid where fluid is going away from us, so it seems to be stuck to the top floor,
right,
and going toward us, which is the bottom. So that's how I see these colors. And the vector fields, and you can freeze them, they help you see this in a detail. You see it maybe better on this figure. The vector fields in this planes tell you that you have some rotation. You can see it here. The field is making a rotational movement.
I see. Yes. And then another quick question about this minimal cell, right? So how do you actually know that the cell captures everything you want it to capture? Like, is there any figures of merit, or you just look at this?
No, it's really we don't have a theory that would tell us with any precision what is a minimal cell. So roughly what you wanted to do in this particular case, you wanted to fit two rolls, because a roll is coming up and has to come down. So that gives you some intuition how wide should be in a spanwise direction. And in the streamwise direction, you want it to be long enough to capture one of these wiggles that you see when you look at this. You see that there's a kind of wiggling. Here it's very organized. I'm lucky at this point, but you can see some wiggle here. So you want to make sure that you have enough of streamwise direction to capture such a feature. But it's empirical. You play with it, and then you publish a paper, and the other people to be able to compare it with you. So this was done by Hamilton, Kim, and Valev in the 90s. They will use the same dimensions of the cell just to be able to compare with your results. But it's totally empirical. There is no, and the modern theory of space-time is supposed to create minimal cells by itself by finding solutions whose spanwise and streamwise periodicities just comes from equations of motion. Doesn't come from imposing artificial boundary conditions. So that was, in one of the previous talk, I was showing you patterns in that case in the one-dimensional flow, but plumbers are not impressed by one dimension. So this is all in 3 dimensions, and this is all experimental accessible fluid dynamics. So how do you hunt? Now, what we learned in this course is whenever you have a dynamical system that you don't understand, the first thing you're supposed to do is you're supposed to find its equilibrium, fixed points. So you're supposed to find state solutions that don't change in time. So how does it work in this case? So there is a classical solution for laminar flows, which is known from 19th century, and it's very obvious. When you have two surfaces moving, what Navier-Stokes says that if I put horizontal sheets of different velocities, then there'll be friction between them. So the bottom and top layer, imagining being just divided in lots of thin sheets, bottom and lower are glued to the walls. That's called no-stick boundary condition. Your intuition is then in the middle, there should be no motion because you feel drag from above and from below. So you expect constant, in this case, green means zero velocity. And then you expect the rest to arrange in such a way that the friction is balanced equally between all the layers. And that's called laminar equilibrium. It's totally trivial solution. Velocity is just proportional to the distance away from the center. And it goes to, let's say, +1 in some units to -1 from top to the bottom. That solution has been known forever. But Nagata discovered a Japanese, well, doesn't matter, a scientist working in England discovered other solutions. And they have some funky names like lower branch, upper branch. Ignore that, it has to do with bifurcations. But he discovered solutions that are pretty stunning, because when you look at these two solutions and you go back to where we started, to this box, in this box you see both of them. So you see a solution, a glimpse of solution that looks like a wiggle down the middle right now, a wiggle down the middle. And now you look at this solution, and one of them looks like straight rolls, and the other one looks like things are falling apart. And what used to be very hard to explain to professors of fluid dynamics and engineering is that these solutions, they're not turbulent. They have features of which we see in turbulence, but they're pretty amazing, because with the eyes, it's a non-trivial disposition of three-dimensional velocity across the whole volume of this thing. And it has a property that I stick it in my time integrator, it doesn't change in time. So even though it looks like it's supposed to fall apart. So these are equilibrium solutions. And by now we know how to get tons of them, and we have hundreds and thousands for different experimental situations, different geometries. So I'll show you a few more just so you get. So basically, there are other equilibria which have more structures, and there are things that look totally crazy turbulent, and they have, but they are equilibria. So that's first thing. Next thing, yeah.
They're unstable, right?
What do you say?
They are unstable.
They're all unstable in the sense that if you make small perturbation on them, they will fall apart and go back into turbulence. And it's not possible not to make small perturbations on them because your numerical codes have small accuracy, etc. But we can quantify exactly like we did in the course. Now that we have equilibria, we can linearize their neighborhoods. I will not show it unless you ask me. And we can compute their eigenvalues and eigenvectors of linearized unstable equilibrium. And they will turn out, the eigenvectors will be, states of fluid like what you see right now. But the eigenvalues will have a property that there will be few in number, 1, 2, 3, 4. I'll show you some plots in which you're unstable. So if you perturb along eigenvector, which is a picture like you're seeing right now, but now it's just the state of flow close to equilibrium. If you perturb in that direction, you fall apart. But the other 62,000 dimensions or million dimensions, they all are negative, so they fall in. So,
but the fluid is incompressible, right?
Yeah, I mean, this is a technical detail of incompressible fluid dynamics, and it actually causes some trouble. So it's easier to work with models I showed you before, like Kuramoto-Shivashinsky, because this incompressibility condition doesn't show up. So there are, conceptual difficulties that come, and that's what makes these codes hard to write and get good, get high quality solutions of the flows. Now I have to tell you that in this calculation, our numerical accuracy can be 1 part in 10 to 11, meaning you have a liter of the fluid, the stuff is moving with velocity of order 1, but the error on velocity field is 10 to minus 11. And if you change the discretization, etc., it turns out it's still very good, but it's 10 to the minus 6. So these things can be solved ridiculously well, especially for the geometries like the planed Cuet and pipe flows. It's very hard to solve them accurately when you have crazy boundary conditions, but here it works. So this was a big deal to be able to find, and that happened in the last century, end of last century, that we could actually find this equilibrium and study the stability for very high dimensional fluid flows, 100,000 dimension. And you haven't asked, but what is the dimension? Whenever you write these fluid flows, in principle, they're infinite dimensional. But if you go to the Fourier-Chebyshev basis, you're forced to truncate this basis. And the dimension in this context of state space just means the number of computational degrees of freedom you're keeping track of as you're solving these equations. They become ordinary differential equations of very high degree rather than dimension, rather than partial differential equations. So this was a big deal to find them, but then, something totally remarkable happened. And that was done by assistant professor in Japan who must have spent, I know him personally, Kawahara, who has spent a great deal of time in a dark room clicking on his simulation of the fluid. And he discovered the first periodic orbit. Now let me show you what periodic orbits are. So this just looks like what I showed you before. The thing that looks turbulent gets almost regular, then it's unstable, fall apart, does something. But if you look at upper left corner, it actually has a period which is 75 units of some or other dimensional units. And we are going through the 75 units right now. And if I didn't tell you it was periodic, you could absolutely not distinguish it from the other solution, which was turbulent. It never came back. Now, this is a remarkable movie. It's a video that plays and then seamlessly replays itself and replays itself, every 75 seconds or whatever time unit you have. But then it turns out there's another one. Again, we know it's different, but to you it might look like a typical turbulent thing. And you can see it's doing something slightly different. And after 88.9 units of time, it comes back. And there is another one. And if you're interested to start to understand in more detail, we have a database. You can just click on it and you can look at, in principle, there are infinitely many of these solutions, but we have tabulated 100 or so for you that you can just run on your laptop if you want to.
So the difference between these and the equilibria that you showed before is that the equilibria in the equilibria the patterns do not change. I mean, the velocity patterns are always the same.
Yeah, and as you'll see later in the tutorial, this is a big deal because equilibrium is just a steady state of the fluid that in principle is there forever. In simulation, it might decay after a while because of the accumulating errors. And, you know, it looks like a snapshot of your fluid. But these guys are more amazing because they look like space-time videos of your fluid. So they're tracking the turbulent behavior of the fluid, not only as instantaneous pictures of the state of the fluid, but they're following also, and you know, we'll make this very explicit, the turbulent fluid for the period of the orbit. So they are a really big deal. And they kind of changed everything. And you know, this happens often in science. Skeptics like myself, reactionaries, people who say, oh, it can't be done, etc. Don't try until somebody does it. And then once it's like a transistor, once you realize you can make a transistor, you know, you can make an industry out of it. And indeed, at Georgia Tech, this is an industry. On the 3rd and 5th floor of Howard, there is a bunch of grad students who do experiments and who do simulations, you know, in great detail, and they can just do it, even though not that long ago we all believed it was an impossible thing to do. So the main thing about these solutions is we computed them in a minimal cell. But actually, they're exact solutions of the infinite system, but they have one peculiar property that they're tiling the infinite system. You can see this here. We have taken 3 copies, you know, sideways, or 4 copies downstream of the solutions I've just shown you, one of the solutions. The short one, actually, I haven't shown it to you yet. And they have the same property which you saw in Kuramoto-Shivashinsky. They tile the volume of the cell in a regular way, which is not what you see in experiment. But then the periodic orbit theory is the thing that gives you connection between such tilings and computing expectation values. Now, because this is a serious class, I'll show you a little bit about stability of equilibrium. And similar, we have data also for all periodic orbits of the same kind. So what's plotted here is a bunch of solutions. So originally, I showed you 5 different steady states. They were called lower branch, upper branch, and then newbie and newbie 2, and then they don't have very interesting names because they start getting numbered. We have so many of them. So on the same plane where we are looking at stability exponents of these guys, and for periodic orbits, we look at Foucault exponents, which is stability of the flow per unit time. So logarithm of the multiply. And because this flow is, its stability is a real matrix, which is 60,000 dimension square matrix. That's its Jacobian or Foucault matrix, depending on what it is. It has its eigenvalues. And the lower branch, blue, had one unstable eigenvalue, one contracting eigenvalue, and the other eigenvalues are of the plot, you know, to the negative. Everything that's negative is stable. So you really care about the unstable directions most. And the upper branch, which you don't remember anymore, but it was the one that looked wilder. That one has actually a pair, a complex pair of unstable eigenvalues. And then it has a bunch of contracting eigenvalues, which are less contracting in this one, because the more negative eigenvalue is, the quicker the transient dies. And the newbie had some eigenvalues, etc. So we have the data on these things, and the main thing to remember is all of them have a finite number of unstable eigenvalues, meaning positive exponent, and infinitely many contracting eigenvalues. And that's the reason why we can do any of these problems, and that's the reason why I can recognize structures. There are very few structures that persist, and everything that's kinky in a fluid is immediately dissipated by these very contracting eigenvalues. So what's striking about these solutions is that now I'm showing you sustained turbulence. And, how would you know? It looks like the other guys. It bounces around and then does this typical thing. It gets organized right now. Right now, boom. You think it's dead? No, it continues. So this should be possible to understand and organize because there are very few features and in these flows, and we can see them by naked eyes. So what do we do? So then there's some physical things you do, which I will not emphasize very much, but there are usual things you should do in physics. You should think of energy, how much of it is, how much you have to burn, which is power input, to keep this thing going, because I have to move this. I have to apply force to these walls to move them, or force per unit per area, etc. And we know that it's a viscous fluid, so I'm losing energy and putting in, I'm losing to fluid. It's basically being converted to heat. And you study that, and that's very useful to develop intuition about the flow. But here is something that most people don't get taught, but it was the fundamental idea of Eberhard Hoff in 1948. You should look at the state space, meaning you should peer into 62,000 dimensions. So how do you do that? So I'll explain it. First of all, you need to produce some kind of coordinate system, and orthogonal coordinates are very useful. And it turns out the fluid has orthogonality built in, because when you look at kinetic energy of the fluid, any place in a fluid, you have velocity fields, and you can define in our three-dimensional frame product of two different velocities. And if you identify this velocity divided by 2, you get kinetic energy. So there is a natural way to produce a vector space with 62,000 directions, which has orthogonality built into it. And so how do you now look at this? So maybe I'll show you this guy first. You can say, well, if I have this equilibrium state, that's a point in a vector space. So it seems like very natural that I use the vector that connects my origin, zero kinetic energy, to that point in 62 dimensions as one coordinate. And once I have one coordinate, then I look at the fluid, and it so happens that this is an unstable equilibrium. So if it has instability, then, for example, it has a complex eigenvalue pair of two coordinates, they define a plane. So that gives me an idea, maybe in this 60 or million dimensions, I go there where my equilibrium is, and there's a preferred plane of instability, and everybody is falling into that. Otherwise, if I only have one pair of unstable eigenvalues, complex pair. So let's see what it looks like. So, for example, we can take this complex pair or this complex pair to do that. And we can look what the neighborhood looks like. And it's amazing. so this is projection from 62,000 dimensions onto 3. And, we have chosen the origin of this plot to be the point in a high dimensional state space where the point is. We have chosen a plane in which unstable perturbations, they spiral out. So you can see things spiraling out. And then we have looked at it a little bit and discovered there is, a nice direction that's orthogonal to this plane, but it captures what happens linearly far away. And what's amazing about this plot is that, and you'll see more sense of it later, when you look at the whole state space, this is roughly, as far as state space goes in this projection. And what happens in this plot is you start running around because you're oscillating. This is an oscillatory instability until you hit some obstacles in that state space, which kind of fold you and force you someplace, and then you do something else. And there's one particular trajectory, the black one, that does all this, and then it dies as a stable equilibrium, meaning zero velocity or zero deviation from the laminar solution. So that's beautiful. And, we are peering into 62 dimensions, and we understand it because you took this course or because you took Strogat's course.
But where's the equilibrium point here?
I'll show you its placement soon. So this was local. So basically, we chose as the origin the equilibrium point itself. And then we chose as a plane a complex pair of eigenvectors that span a plane. You learn this looking at instabilities in lower dimensions. And then to capture the non-linearity, the fact that this system is not just flat, you don't just spiral out, but you have to bend, just like you have to do in Roslet and Lorentz flows. You found obstacles in state space you had to bend, and that's what nonlinearity does. But that's local, and more amazing is what we do next. We will actually have a global one. And here is the idea of global thing. I just told you, when you have a point in a state space visualized in 3 dimensions, it looks like a recognizable solution of the flow. So that's, one of the equilibria, which we call upper branch. And I showed you this picture at the very start. So this corresponds to point in a state space. Now, this system has symmetries, just 2 planes against each other. So, for example, you can rotate these 2 planes that are 3-dimensional world by 180 degrees. And when you do this, they still have the top one is still going away from you, and bottom one is going behind you. So you can do that. Then you have a regular paving in a spanwise direction, and you can actually move your solution, by the half of the box. And every time you do this, you get things that look very different. So, so this solution, UB, has been translated by the half-width of this periodic domain and flipped, I think. And this solution is the solution above that has been flipped, and it has a totally different shape. And then when it's translated by half, it has a totally different shape between 4 of these things. So from one solution, and we are used to this whenever you have discrete symmetries, from one equilibrium, you get 3 more for free just by symmetry. But they're very different in shape, which means that when I present them in the state space, they're very distant from each other. Now, I can use these guys and I can add them up and subtract some and add some, and I can show that these combinations are orthogonal under this norm that we constructed, the energy norm, which means now that out of this one solution plus symmetries, I get 4 vectors in a state space. They are 62,000 dimensional vectors, which are orthogonal to each other. And so they are very far apart from each other. They point in totally different directions, but they have been constructed from the solution of the system. So we have right to hope that they will span the important part of the state space. And when we look at these 4 dimensions as opposed to 62,000 dimensions, maybe we'll see something. Let's have a look. And these are kind of things which you do when you decompose things in Fourier modes, but now it's non-linear. It's not some trivial thing. You actually have to solve your Navier-Stokes equations with high precisions. And when you add them up, you get something that doesn't look like a solution, but is a point in the same state space. And for other ones, you get shapes like this. And now what you take is you take your turbulent flow and you project your state onto these 4 coordinates. Are you with me? For example, if I have my fluid flow, here it is, and it's doing its turbulent thing, I can project it onto the base 3, this particular base. And projecting it means it's this orthogonality relation. I multiply these two 64,000 dimensional vectors, and I integrate over all components. Remember what the norm was, and I get a number. It says how much of this fluid state is contained in this direction. I'll remind you what the form was, I take my 64-dimensional vector, which is my turbulent vector, I take a basis vector, I multiply them, I get a number. And that number is projection of a big vector into one of the 4 dimensions I care about. So what happens? It is amazing. So I'll show you. I just take 2 of these vectors and show you what happens. For the turbulent flow you've been looking at all along. Bango, you get Starship Enterprise. So now this answers Domenico's questions. The points in this plot are the equilibria we've been studying. So this point here, which we chose to be the origin, is the laminar solution. It's the first equilibrium in these 4 solutions that I showed you. Then there is this thing called upper branch, which was, wiggly but static. It's hiding in there. There's a thing that's called lower branch. Now, lower branch had only one unstable equilibrium, So if I start along the unstable direction of lower branch equilibrium, in one direction, it just goes and dies. That's this blue line. In other direction, I kick it into the turbulent world, so it actually visits this upper branch and eventually dies. If I there is this newbie, which is in the center of the system, which seems to be taking stuff and shrinking everything from 64 dimensions and then spewing it, spiraling out in the plane, and part of it goes toward lower branch and dies, and the other part goes up, etc. So suddenly you have a visualization of what these solutions meant. When we had them individually, it was very, after a while we got bored of them because they all looked like, for some part of time, they look organized, but then they go bananas. But in this dual representation, global state space, you can actually see where they go, who they visit. And that means that you can tile your huge dimensional state space by neighborhoods, and every neighborhood has a name. In this case, the first set of neighborhoods, am I coming close to one of these equilibria? This is in 2 dimensions, but we have 4 at hand in this contraction. So here is what, and now you have to understand this picture is not static. This is actually 1,000 videos put together. Because every one of these lines that you see is one of the simulations I've shown you, projected onto 4 coordinates. And if you look at it in 3 dimensions, this is a problem. You start seeing very interesting things. In 3 dimensions, there was this multiplicity because I could flip the system this way and sideways, streamwise and spanwise, and it was same system that was invariance of equations of motions, boundary conditions. And that meant that some equilibria, like the dead one, laminar one, just mapped into itself, but other ones mapped into 4 or 2 copies. So the upper branch has 4 copies. And what's plotted here are various equilibria. There are various dots here. But also what's plotted in is a turbulent flow, the flow that I showed you first that just goes on forever. And what we do here is we strobe it. Every time it runs a little bit, we record it as a dot on this plot and just let it run for a while. And what you see from this plot is that turbulence is chaperoned by these upper branches, unstable manifolds. It doesn't, they seem to push it back in. And, you're not allowed to go down here either. So we are starting to see not only that we can give names to things, but we can start understanding how this turbulence works in a state space. It's localized to something.
I didn't understand one thing. When you choose the projections, right? For example, in the phase space and state space picture, right? You're taking the inner products of them.
Yeah, so it's just like usual vectors, except they're very high dimensional.
Right, and so these
you know this from quantum mechanics. You have eigenfunctions, and you write your wave as a sum of a projection on the eigenfunctions. So it's same. It's just amazing that you can do this in fluids, because usually you don't have a natural normal, natural orthogonality in fluids.
Right. So these E1, E2, E3, these are also like
these are states of the system which are orthogonal. And they're being
And
constructed by using our tricks on projection operators. Because we had 2 discrete symmetries, we had 4 projection operators.
it turns out that it's a very good choice, because at least in the example that you showed, you can visualize the whole trip
I mean,
along
if we were in heaven, you can imagine, because before that, turbulence was a horrible thing. And when you look at fluids, you don't expect these rigid structures you see in the state space. Stable, unstable manifold in state space are like, coat hangers. I mean, they're really there. When you look at the fluid, it just looks like some sloppy stuff that's sloshing around. So that kind of visualization of fluid we found totally amazing.
So how were those states built? I mean, how are they chosen? The orthogonal.
We just chose the first state that looked like it was typical of turbulence, first equilibrium. And from it, we got 4 vectors by symmetry. And then we projected on the 4 vectors, and suddenly we could see everything. So this is an incredible luck. Because usually, I mean, in 100,000 dimension, everybody's height of everybody who is normally 6 feet is, in 100,000 dimension, it's 6 feet divided by 100,000. There was an exercise in Chaos book. So everybody looks very small in 100,000 dimensions, unless you know to go there and orient your stick along the height of the person, and then you get, a big thing. So that's what this choice of coordinate does. It says dynamics chooses this neighborhood. Inertial manifold is pinned down by this neighborhood. And if you go to that neighborhood, the goal is over there. I'm the referee, I go to the goal, and then I can see, all the distances very clearly. So that's the idea. And the main thing that's unusual about it is you have to solve highly nonlinear equations to find these points. But once you have them, you can triangulate the neighborhood in terms of them. And that's, why we recognize clouds. These shapes show up here and there. And they're, mental points that make the whole object recognizable. Even though in between it's changing shape in crazy ways. But then the periodic solution follow it dynamically for finite time. And they enable us also to triangulate the parts of space-time that are very hard to understand otherwise, because humans don't remember these videos very well. That's hard for us to see. So let's work this out in more detail. So here is the utility of this new visualization, in which we can think of the same system in terms of infinite dimensional state space on the left and our physical intuition in 3 dimension on the right. So what we do now, we start with a newbie, one of these equilibrium positions, and run our simulation, and nothing is happening. But when we look into the state space, we see actually there's a little motion. Doesn't look like anything here. And the newbie is unstable, so I run away from it. And the fluid is really changing. And it's starting to look like the lower branch. Then I go bananas because I'm coming close to upper branch. And I'm doing all the crazy stuff that turbulent fluid does. And I do all these things we have seen in simulation, but now we know where they're in state space, and we can start exploring them in detail. And the way this is plotted is that I keep just a finite history with me, so I don't fill up the space is this red line. So now I've slowed down, my tail is very short. But no, I get kicked out again. So now I'm going really fast, zipping all over the place in 60,000 dimensions. And this goes on for a while. So I'll just stop. And finally, I find a hole where I can escape the turbulent world. And I calm down. And I calm down. And eventually, this thing dies and becomes our equilibrium that we cared about before. So now we have a tool where we can combine our intuition as a plumbers in 3D with our, amazing tools of nonlinear dynamics in state space. So there is a narrative here. I gave you some glimpse. Now comes the next thing. I told you that we are able to find periodic orbits. So the way this is done is that we run a simulation. So here is a time, typical times I showed you before, order 20 to 100. And here we are running something to 1,000. And what's color coded is how close am I at a given time to my history 50, 100, 150 units back. And if I'm very close, it's a very dark region. And that means that my state has a recurrence. It's come very close to it because the distance between the two states has become small. So in the work that our numerical fluid dynamicists do on the 3rd and 5th floor and all over the globe, they take these states which are very close to themselves and they say, well, this means that I come back to myself 57 units before and actually know the shape of the state. So they put it into the searching routine, Newton routine, or some fancy routine, and actually find this periodic orbits. So they are marked. What you find from initial gases are marked by dots and triangles here. So that's how periodic solutions are found, by finding first close recurrences. And here is the dual visualization of a periodic solution. So what's happening, this is turbulent, this is periodic orbit. Periodic orbit is orange in state space. When I'm black, I'm close to it, and you can't tell by eye the difference between them. So I'm shadowed by a periodic orbit. Until ... I run away, and periodic orbit does its thing, but I'm just doing my turbulent thing. So that illustrates the crucial part of why we use periodic orbits to describe chaotic or turbulent systems. They're shadowed by periodic orbit, and if you have a good theory, which is periodic orbit theory, you can turn this into computation. So you can compute all the averages computed on periodic orbit by averages computed, on ergodic orbit, by averages computed by turbulent orbit. So this is totally beautiful and stunning. And in next simulation, I showed you originally that it looked like the upper branch had this unstable equilibrium planes or, semi-spheres. And the turbulent flow seemed to be captured, chaperoned by them. Now we can see how this works by simulations where you have a periodic flow and how it visits various neighborhoods. And you realize that actually now it's behaving like this neighborhood, and now it's behaving like some of the crazy stuff in the store. So while the unstable equilibria of Navier-Stokes captures some features of the flow, the unstable periodic orbits of Navier-Stokes actually are embedded in turbulence C, and they capture great deal of what you see. So here's another example. This is a solution that does a little twiddle dance, doesn't have a symmetry, goes over there. So it's different from the one I showed you before, and it's exploring different part of the state space. Here is another, totally amazing thing which I showed you originally, but now we'll look at it in detail. What happens if I start close to this newbie, this equilibrium here, and what's happening in the real space? And what's remarkable is when I look at the cross section of the flow, this is wall normal and span-wise direction you're looking at. Streamwise is right into this place. I have a two-roll state. As I leave it and I march on unstable manifold to the equilibrium, it rearranges itself like Houdini and becomes, a one-roll state. I mean, there's a red roll and blue roll, whereas this had much more complicated feature. There's, four rolls basically in here when you look at it. So you can start understanding how the geometry of, transitions between different regions is by understanding it in the space and understanding it in the state space. So we have amazing, powerful tools to, map out turbulence and illustrate it. It's immense amount of work. Doing this for fluids is much harder than doing it for one-dimensional Kuramoto-Shiransky example. But it only counts in engineering community if you can do it for the real case. And we can do it, and you can do it. So to summarize, it used to be that turbulence was a bunch of things. Originally, people had wind tunnels, and they would put one hot wire in the wind tunnel whose resistivity would change due to the cooling by the turbulence of the wind going through the wind tunnel. And that was all they could say about turbulence. They measured some fluctuations in three-dimensional flow. Today, it's totally amazing. When you have an experiment, you can extract from it very detailed three-dimensional velocity data as a function of time. It could be terabytes of data, but if we know how to extract it, analyze it, close it. And we have a theory that says this is all suspended on a very rigid skeleton of equilibria and space-time periodic solutions. And now that you have this, you can design things or control things because you understand the stable, unstable manifolds of these solutions, which tell you how you have to affect the flow in space-time, what kind of perturbation you have to give it to control it or make it go someplace where you want to go in state space. And if you are interested in how to decrease consumption of passenger jet crossing Atlantic, from this solution you don't have to, in best of all possible worlds, you don't have to simulate the whole jet. You can use these solutions to compute dynamical averages that you've learned about and find out how to control it. And this is, I'm using fluids because we can all visualize fluids, but honestly, I would be much happier to illustrate it on Young-Mills theory and explain quark confinement or particle masses or many other things of strongly nonlinear coupled systems. And someday maybe we'll be able to do it. And maybe we'll make better cardiac devices, pacemakers, etc., using these ideas. So that's what this course was really about, but we just gave you tools to do it. What needs to be done is ahead of us, as is always our life in research. And you're very interested in this. You can read some of the literature, and you can click on this link for channel flow. Download the simulation software and do all these calculations I showed you here. And it's not hard anymore. It's a high-level language. So one of the most interesting unfinished projects we have in our group was done by undergraduate senior who learned how to use it. It takes a few weeks to learn this, and then did some very interesting work.